Hi, this is Tzvi Rosen with another course in the MAS 6318 course. We discussed some constructions using compass and straightedge in the previous lectures, and now we'll talk about how we transition from compass and straightedge, which are really just geometric tools, to the toolbox of algebra, which uses numbers and equations to study these shapes. So let's get into it. We start with Euclid and Descartes. Euclid wrote the Elements around in about 300 BCE Greece, though we don't really know for sure. And in Euclid's Elements, everything is pictures. Okay, there's no such thing as a fixed length. There's only a segment and the ratio of the lengths of two segments. There's no such thing as, this is one is 1 inch long. That's we don't. He didn't really study things that way. Everything was relational. Everything was geometric in pictures. And then we have Descartes. It's around 1600 in the Common Era in France. And for Descartes, Descartes was the one who introduced the innovation of having numbers to describe locations. Okay, so everything with Euclid, everything is pictures. Let's use a different color here. Okay. And then we have Descartes, for whom numbers can describe locations. And we're going to go with specifics into what we mean. Okay. So in particular, we have the first case where we can use numbers to describe location is on the number line. So we can talk about marking a line with numbers, stepping forward one integer at a time, okay, and if I have 2 points on this line, this number line, I can describe them using a certain number. Okay, so let's say that's 1.75, and then we'll get something like here. Let's say this is minus 2.1. Okay, and then we can compute the distance between those 2 points. So by taking 1.75 and then subtracting the other number, minus 2.1, to obtain 3.85. Okay, and that would tell me this is the distance between the points on the number line. Okay. Now we can move from the number line, where everything is kind of simple, like you have a specific number corresponding to each point, and then you can take distance by subtracting. Things get a little more complicated in the Cartesian plane. So in the Cartesian plane, pairs of numbers or coordinates describe locations. So for instance, okay, this is given by the coordinates 0, 0. And then we can get another point, for instance, the point 3, 4, by walking along the horizontal axis as if it's a number line. So you walk along 3 units, and then you walk up 4 units. Okay, so going right 3 units, followed by up 4 units, gives you the point 3,4. Okay? And I could also go in a different order. There's nothing telling me I have to go first right and then up. I can also go up and then right. So go up 4 units, right 3 units, and you'll end up at the same place. Okay, and let's write another point. Why not? Let's put this point is -1, 1. Okay, because you go left 1 unit, and then you go up 1 unit. So this is left 1 unit, and this is up 1 unit. Okay, now how do we think about distance in this formulation? Well, if we want to compute distance, so we have to compute a hypotenuse of a right triangle. Okay, and specifically it's the right triangle whose legs are the blue dotted edges here. Okay, so for distance, from 0, 0 to 3, 4, you use the Pythagorean theorem to get 3 squared plus 4 squared equals d squared, where this is d. And you find that this is 9 plus 16, or 25. Okay, and then you take the positive square root to get d equals 5. Okay. What if I wanted to compute distance between 2 points and one of them isn't the origin? So we can go back to the previous slide. Oh, oops. Here we go. So okay, so let's say instead of going from 0, 0 to 3, 4, I'm going from -1, 1 to 3, 4. Okay, so let's mark -1, 1 again. There we go. And we can go between these 2 points using, again, lines parallel to the horizontal axis and the vertical axis, and then use that together with the Pythagorean theorem to obtain the value of d. So here, how far am I going in the up direction? So this up, let's make this a and b, and instead of d, why don't we go crazy and call it c? So a is going to be equal to 3 minus -1. Okay, and here we're using, 3 minus +1. Not even that. 4 minus 1, because you take the y values to get a in this case. So that's like you're traveling along the number line in the y direction. So we get 3. And then b is given by the difference in x values, again, traveling along the number line in the x direction. So we get 3 minus -1, which is 4. Okay. And, surprise, surprise, a squared plus b squared equals 3 squared plus 4 squared, which is 25 again. And so here, even though it's a different triangle, we get that c is 5. Okay? So here we used a formula for distance. The distance from point 1 which is x1, y1, to point 2, which is x2, y2, can be given by, so if you write d equals the square root of x2 minus x1 squared plus y2 minus y1 squared. Okay, so that's how we get a distance formula using Pythagorean theorem. And so now we're talking about distances between points, and the numbers, a pair of numbers assigns a location to each point, and then all of the operations we're doing are just arithmetic operations. So we don't have to do all of the Euclid tricks with compass and straight edge. Okay, and let's make that more explicit. So while we have, so now that we have numbers describing our locations, we can start to describe our geometric figures using algebraic equations with those numbers. So we'll look at two examples of that. So for instance, with graphs of functions, if you have y equals f of x, okay, so what that tells us to do is you're looking at all points in the plane of the form x, y, where y equals f of x, where this equation is true. Find the pairs of points x, y such that y equals f of x. Okay, and then let's say in this case x is f of x is x cubed. Let's make it x cubed minus x. Okay. So then your function will look something like that. Okay. So this is an example of a graph of a function which you can get by specifying points satisfying a certain equation. But you don't have to have this set of points being specified by a function. You could have just any equation involving the two coordinates of your point. And here's an example of that. If I have y squared equals x cubed plus, let's make it, yeah, x cubed plus x squared. Okay, so it's actually pretty similar to this, but the y is squared, and instead of minus x, we have plus x squared. So if I want to look at the corresponding graph, it looks something like this. Okay, so this is not a function. Not the graph of a function. But it is a perfectly lovely geometric figure described by the set of points satisfying this equation. Okay, so it's valid as a geometric figure. Okay. So now that these geometric objects are being described by equations, we can think about what happens when those geometric objects intersect each other. Okay, so specifically, if two geometric objects are given by f of xy equals 0 and get this on its own line, g of xy equals 0, then how can we describe the intersection of the objects? Okay, so let's look at an example. if we have the graph of y equals x squared, and we have the graph of the line y equals x plus 1, and let's make this one magenta. Okay. Then when we graph these two functions, they do intersect. So this lives over here. So something like this. Okay. So our intersection points are here and here. Okay, well, how might I find what those intersection points actually are? Well, the thing that I know about these two intersection points, okay, I know that both live on both of these graphs, which means that both of these equations are satisfied. So they are simultaneous equations. Y equals x plus 1 and y equals x squared. So I can solve them like a system of equations, and I can combine them. So because we have a value for y in both equations, I can set them equal to each other. So we have x squared equals x plus 1. And then you can solve x squared minus x minus 1 equals 0. And using the quadratic formula, that will give you your x, at which point you can plug in your y. So that's what we're going to be doing going forward whenever we want to solve for the points of intersection of two figures. We're going to consider it as a system of simultaneous equations. Okay, so let's think about this in the case of a line. So we know that whenever we're talking about lines, these are given by linear equations. So those are of the form ax plus by equals c. Okay, so you might say, why don't you just use y equals mx plus b? Well, then you run into the problem of the vertical lines, and so this way covers all cases, though it is a bit redundant. So if I have, for instance, 2ax plus 2by equals 2c, then these two describe the same line. Okay, but as long as you keep this in mind, I'm going to use this form for the equation so that we know we can cover all the cases. Okay, so let's say I have two equations for two different lines. Okay, so ax plus by equals c and dx plus ey equals f. Okay, so how might I solve this? The same way you would solve any system of simultaneous equations. You can combine them. You can solve for one and substitute it into the other equation and solve what comes out. So let's do this by taking d times equation 1 and subtracting a times equation 2. Okay, so what do we get? We have by equals, bd minus ae y equals cd minus af. Okay. And specifically, y equals cd minus af divided by bd minus ae. Okay. So now we have our value for y. Okay. And if you were going to stop me and say, what if bd minus ae is 0? You would be completely in the right to do that, but we're going to set aside that case. for now. Okay, and then you can solve for x as well. You can either plug this into one of the equations, or you could do a similar trick by taking e times equation 1 and subtract b times equation 2, and you would obtain AE minus BD times x equals CE minus BF. Okay. And then you would get x equals CE minus BF divided by AE minus BD. Okay, and of course, if BD minus AE is 0, then so will AE minus BD be 0, but we're setting those cases aside. So what this tells us is that in really general situations, when I have two lines, I can find a unique point of intersection xy where both of those equations are satisfied. Okay, and that makes sense if you think about what most setups of lines look like. And, you know, so like, for instance, okay. So now we should consider what happens if AE minus BD is 0. Okay. I told you I would talk about it. So if we have y equals AX plus by equals C, and dx plus EY equals F. So what's the situation where AE minus BD equals 0? Okay, well, someone who's taken linear algebra might recognize this as a determinant. This is what you would get let's get a new color. This happens when the vector AB is a multiple of DE. Okay, so in that case, you won't get a unique solution to the point xy. Okay, so let's take that a little further. What does that mean about parallel lines? Okay, what have we figured out so far? So we know that if two lines are parallel, they don't intersect. But using our tools of deduction on the equations that we have for the lines in the Cartesian plane, we have a unique point of intersection from the formula. So how can we account for the cases where the lines don't intersect? Well, what happened on the last slide? If AE minus BD equals 0, then we don't have a unique point of intersection. Okay, so what does that mean? That means either we have a lot of points of intersection, or we can have no points of intersection. But we know for sure that if two lines are going to be parallel, then they have to have AE minus BD equals 0. Okay, so let's say AE minus BD equals 0, and as we said on the last slide, this is that DE is a multiple of AB. So let's take that to be true. So we have ax plus by equals c, and then just a scalar multiple, so let's make that multiple given by a Greek letter lambda. So lambda ax plus lambda by equals d. So if we want to solve these equations, see when these equations are both satisfied, we can take lambda times equation 1 and subtract equation 2. And what we get is 0 equals lambda c minus d. Okay, so this equation tells me that either, let me type this out, either lambda c minus d equals 0, and it doesn't matter what x and y are. So either this is always true or always false. Okay? In the case that it's always true, then we just have the same line described twice. If it's always false, then they must be parallel. Okay. Okay. So just shifting things around a bit. Thanks for your patience. So what we find is that two parallel lines are lines that have the same coefficients or just scaled coefficients for x and y, but then the constant term doesn't agree. Okay. Okay, so in particular, so if you have lines of this form, oops, given y equals mx plus b, and let's say these are two different lines, so let's call it let's make this y equals ax plus b and y equals cx plus d. Okay, so putting this all into the form we saw previously, so we have minus ax plus y equals b and minus cx plus y equals d. Okay, so we know that this is supposed to be a scalar multiple, so we have because the coefficient of y is 1, that means that a has to be equal to c. So parallel means a equals c, and furthermore, b equals d. Sorry, if b were to be equal to d, then they would be the same line. So furthermore, b is not equal to d. Okay, so right now, just using the fact that parallel lines don't intersect, and using the fact that we can describe our lines with equations of this form, we have characterized pairs of parallel lines as being lines with the same slope and different y-intercepts. Okay, well now let's talk about perpendicular lines. Okay, and we've spoken a little bit about what it means for lines to be perpendicular. They meet at right angles. That's the simplest version. So let's say I have a line given by ax plus by equals c. How can I figure out if another line dx plus ey equals f, how do I know if these two are perpendicular? Okay. Well, I'm going to try and simplify this by by putting everything at the origin. So we know that moving a line horizontally or vertically doesn't affect whether or not this pair of lines will be perpendicular. So we're going to assume it's okay to start out by simplifying the problem by moving both lines to the origin. Okay, in other words, we're going to assume C and F are 0. Okay, and you can convince yourself that this doesn't affect the property of being perpendicular. Okay, so now what we're looking at is two lines passing through the origin, and we're trying to figure out if they're perpendicular. So let's see well, first of all, what do we know about these lines? We have ax plus by equals 0, and cx plus dy equals 0. Okay. Let's suppose for an instant that, for a moment, that these two lines are perpendicular. Okay, so we're going to suppose that these are perpendicular. Okay, well, what do we get when we put this right angle here? Well, we know that if we drop a line here parallel to the y-axis, I can describe this triangle pretty well. Okay, so this is the point. If x is 1, this is going to be the point, plugging in x equals 1 to this equation, we would get minus a divided by b for our y-coordinate. So we have 1 minus a over b. As for here, we would get 1, and by the same token, we have minus c over d. Okay? And so you might say correctly, what if b or d is 0? Okay, so that we can kind of cover in a aside. So if b equals 0, then the equation is x equals 0. And the only perpendicular line through the origin is y equals 0. Okay? So we kind of have that characterized, so we can kind of ignore that possibility. So we can assume that b is not equal to 0. Okay. So now that we have a triangle, a right triangle, we can use the Pythagorean theorem to see if we can compute any of our, to find some equation that these values must satisfy. Okay, so I'm going to save some time here. I'm going to replace minus a over b with f and minus c over d with g. Okay, so we have on the hypotenuse, we have f minus g. Okay, so the length of the hypotenuse equals f minus g. How about the length of the two legs? Well, this, we know that we're looking at a vertical line through the x-axis, so that gives us two right triangles. So this one is going to be the square root of 1 plus f squared by the Pythagorean theorem. And this one is going to be the square root of 1 plus g squared. Okay? And then this is f minus g. So the Pythagorean theorem would indicate that if you have square root of 1 plus f squared squared, and you add square root of 1 plus g squared squared, then you should get f minus g squared. Okay, because that's on the hypotenuse. Well, let's expand. So obviously this is the same as 1 plus f squared plus 1 plus g squared equals f squared minus 2fg plus g squared. Okay, and canceling out like terms, simplifying the equation. So we cancel out the f squareds, the g squareds, and we're left with minus 2fg equals equals 2, right? Because we have two 1s here. So that tells me that fg must be equal to minus 1. And the conclusion from all of that calculation just now, again, assuming very little except the Pythagorean theorem and the ability to describe lines using these equations, our conclusion is that two lines are perpendicular, okay, if and only if one of two cases. So we can have one is vertical and the other is horizontal, or the slopes are negative reciprocals of one another. Okay, and that's something that you may have learned in high school without fully deriving, but if you have two lines that are perpendicular, their slopes will be negative reciprocals, meaning that when you multiply them together, you get negative 1. Cool. So let's take that and keep moving. So we've now described equations of lines. Let's describe equations of circles, and I'm sure you've seen this previously. So we know that the definition of a circle, the set of points x, y, all having the same distance from a fixed point hk. Okay, so let's let that distance r, which is the radius of the circle. Okay, so we can translate that into an equation. If we're looking for all points xy having that distance from the point hk, so we learned earlier that the distance formula can be derived from the Pythagorean theorem to get square root of x minus h squared plus y minus k squared. This is the distance from xy to hk, and this will be set to be equal to r. So we don't love square roots, so let's square both sides of the equation to get x minus h squared plus y minus k squared equals r squared. Okay, and this is the equation defining a circle. Okay, and as you can tell, there are 3 degrees of freedom. So you have your x coordinate of the center, y coordinate of center, radius. Okay, so 3 parameters defining the circle. The center is given by hk, and the radius r. Okay. So now let's think about what happens when a line meets a circle. We spent a lot of time discussing lines meeting lines, but now let's discuss lines meeting circles, which is more complicated. So let's say we have our axes. Let's draw a nice circle here. We're going to do like this. Okay, this is a nice big circle, and now we can get a line. So a few different things can happen. So in the red line I just drew, there is no intersection with the circle. Okay, with this green line, there's exactly one point of intersection with the circle, but it's kind of a funny point. It doesn't just touch the circle, it doesn't intersect the circle, it kind of hugs it. Okay, and let's do one more, this pink line. Okay, and this is an honest line intersecting the circle. You know, it really cuts right through it. So let's consider all three of these cases. So in the case, so with the red line, that's describing empty intersection. No points. Okay, the green line describes one point of intersection, but it's like it's a special point. Okay, and finally, the pink line, we have 2 points of intersection. Okay, and by kind of wiggling these lines around in your head, you'll probably be able to convince yourself that this is the only set of possibilities, either 0, 1, or 2 points in the intersection. Now, why would this be? Well, let's think about what's happening in terms of the algebra, right? We have x minus h squared plus y minus k squared equals r squared, and then we have the equation for the line ax plus by equals c. Okay. So let's take these equations and let's see how we can solve them as a system of simultaneous equations. The easiest way to do that will probably be to solve for x or y here and plug it in. So let's assume that that a isn't 0. Okay, so we're going to make that assumption, which if it's not true, you can cover that case separately. So then we're going to have x equals c minus by divided by a. Okay? And now we can plug into the first equation. So we have c minus by over a minus h squared plus y minus k squared equals r squared. Okay. And now let's expand. So we have, it'll probably be easier if we factor out 1 over a squared here. So we have 1 over a squared times c minus by minus ah all squared plus y squared minus 2ky plus k squared equals r squared. Okay. And now I'm going to expand this square. So we have c squared plus b squared y squared plus a squared h squared. These things get a little tedious. Maybe if you know how to use symbolic algebra software, this is your time to do it. But let's go ahead and do it for real. Minus 2bcy minus 2ach plus abhy. Okay, so that's what comes out of here, and that's 1 over a squared. Okay, and then we have the rest of the equation, plus y squared minus 2ky plus k squared equals r squared. Okay. And again, I don't love having fractions, so let's just multiply through by a squared. So that gets rid of a squared here, and we have to add it to the rest of the stuff. A squared minus 2a squared ky plus a squared k squared equals a squared r squared. Okay, fine. So now we've got to keep in mind that we're trying to solve for y. Okay? So solving for y. So let's group according to y. So we have y squared terms. So let's group all of the y squared terms. That gives us b squared plus a squared times y squared. Okay, I think that's all of the y squared terms. Now let's look for the y terms. We have plus abh minus 2bc minus 2a squared k all times y, and then the rest is the constant term in this equation. So we have plus c squared b squared y squared plus a squared h squared minus 2ach. Okay, I'm ignoring the y terms. Plus a squared k squared. Okay, and I'm going to move the a squared r squared onto this side of the equation. Minus a squared r squared should be equal to 0. Okay, so that's a lot. So I'm going to copy it onto the next slide. Okay, so what do we have here? Well, we have a quadratic equation in y. All of these are constant. All of the other letters are constants. You can just plug them in and then solve for y. Okay, so if this is our, let's call this alpha. Call this alpha. You know what? Let's make this alpha 2 because it's the coefficient of y squared. This will be alpha 1, and then this will be alpha 0. Then our equation will be y equals negative alpha 1 plus or minus the square root of b squared minus 4ac gives us alpha 1 squared minus 4 alpha naught alpha 2 divided by 2 alpha 2. Okay? And this will give us our solutions for y, and then we know that x is unique in terms of y. So as soon as you have y, as soon as you choose the solution of y that you want, then x is already fixed. So now we kind of understand why there are 2 points possible for intersection of the circle and the line. So if the discriminant inside the square root is positive, then you get 2 solutions, and that leads to 2 points of intersection. Okay, if the discriminant is 0, then you get a unique solution. But and so that describes the case where you have exactly 1 point of intersection. If the discriminant is negative, then no solutions, and that describes the case where the line does not intersect the circle. Okay, so again, these are geometric facts which you can also deduce from the algebra. Okay, so you thought the line meeting the circle was complicated. Now we get to circle meeting circle. Okay, so let's write down the equation for 2 circles. Equations for 2 circles. We're going to have, well, actually, let's before doing that, let's draw the situation. So we have blue circle. Okay, and now let's think about how other circles might meet it. So theoretically, they could just ever so gently touch. they could intersect in 2 points, and that's kind of about it, right? Oh, and of course you can also have that they don't touch at all. Okay, so again, it's 0, 1, and 2, so it's kind of similar to what we saw with the line in the circle. Okay, so let's consider equations for 2 circles. And I'm going to write down that we're making note of the fact that we have 0 points of intersection here, 1 point here, and 2 points here. Okay, so when we take the equations for 2 circles, we have x minus h squared plus y minus k squared equals r squared. And let's make this h1, k1, and r1. And then the second one will give you x minus h2 squared plus y minus k2 squared equals r2 squared. Okay, so with the line, I had an equation where I could solve for one variable and plug it in. But here, it's not so simple because we have degree 2 in both variables in both equations. So we're going to try one of the other tricks for solving equations, and that is we're going to cancel by adding together scalar multiples of the 2 equations. So in this case, we know we're going to have an x squared term in the first equation and an x squared term in the second equation. So we're going to try and cancel out that x squared term. So we're going to take equation 1 minus equation 2. We're going to see what happens. So we have, multiplying out, we have x squared minus 2h1x plus h1 squared plus y squared minus 2k1y plus k1 squared equals r1 squared. And we're subtracting this one, minus 2h2x plus h2 squared plus y squared minus 2k2y plus k2 squared equals r2 squared. Okay, and let's bring this to the next page. So what we'll get when we subtract we'll get the x squared terms canceling, as well as the y squared terms canceling. Okay. As for the rest, what do we get? So we have 2 times h2 minus h1x. Okay, and we'll group, plus h1 squared minus h2 squared. And then plus 2k2 minus k1 y plus k1 squared minus k2 squared equals r1 squared minus r2 squared. Okay. And now what we have is a linear equation in x and y, right? These are degree 1 terms in x and y, and everything else is constants. Okay, so this is a linear equation. So we can solve for x as ay plus b, okay, where a and b are some function of the h's and k's and r's here. Okay, and so once I have x equals ay plus b, which I'm deducing from these 2 equations being simultaneously true, I can plug that into one or the other equation, and then I'll get something that looks like ay plus b minus h1 squared plus y minus k1 squared equals r1 squared. And this is a quadratic equation in y, so that will have two solutions. That will have 0, 1, or two solutions. In y, which explains why, again, we have 0, 1, or two solutions for the intersection of these two circles. So let's summarize what we've done so far, and we'll pick up this topic with the next lecture. The first point is that numbers can be used to describe locations. Okay. The second is that using those number locations, geometric figures like circles or lines can be described by equations. And finally, you can describe intersections of figures are solutions to systems of equations. Okay, and we had some practice computing those solutions in a few special cases. In the next lecture, we'll talk about what types of numbers will be solutions to the systems of equations, depending on what those equations look like, whether we're talking about circles, lines, etc. And if you're starting with equations that have integers as their coefficients, will you always get integers as your solutions? Maybe rational numbers, maybe something that's not rational. So we'll see that next time. I look forward to seeing you then.